known cross sections. So yesterday, remember we looked at these, we actually made our own. Okay, so basically the idea behind known cross sections or volume of a solid with known cross sections is that we're taking a 2D shape like this triangle. Okay, we're laying it on its side and we're stacking a shape on top of it. And so in this case, we stacked those squares. Remember, we stacked a square like this. And then we said, let's figure out the volume of each of those squares, right? So for some of you, you had like 8 squares. So we can say this one, we'll just do 5. So this one is kind of like this. If you can imagine that this is 3D, because 3D drawing, I mean, no drawing is very good for me, but like 3D drawing is like the worst. I'm so bad at 3D drawing.
And like cubes and stuff?
Yes. So this is like a 3D, like imagine this coming up off the page, right? And then here's another cube, or I guess it would be a rectangular prism coming up off the page. Can you imagine those coming up like this?
No, but you can continue.
Okay, so if I went like this, it's a big, like the squares you guys put on yesterday, okay? So if we wanted to find the volume of this piece that comes up off of the page, what I would do, remember to find the volume of any prism.
Is it like, how far off the page does it go?
The same length as, because it's a square,
Okay.
it's going to come up off the page that exact same length. So, like, I need to like take a class in 3D drawing because I'm so bad at it. That looks so much worse. I'm sorry, I can't draw 3D. Hi.
When did you prep so I can put that? Where's the right?
6th.
6th.
Thank you.
Come find me.
I will.
I forget because I keep forgetting.
Yeah, no, you're fine. You're fine. That's probably, yeah, that's the only day on our class I'm not using it. Okay, so these are like these 3D pieces coming up like this, okay?
Mm-hmm.
So if I want to find the volume of that piece, it has a base that's a square. That's the piece that's going up like this, square, okay? And then remember, it has a height. Okay, let's pretend that I mean, it looks a little bit more square-like than it could. So this is this right here, right? How do we find the volume of something like that? Yeah, we do base times, or length times width. We can say those, length times width times height, right? That's how we find the volume of any cube, which, because we would take the base, the volume of the base, or the area of the base, right, and we multiply it by the height, which means like I take these squares and I would just stack a bunch of them up. That would be the volume of that. Okay.
Now, are we saying this is a perfect cube?
This is not necessarily a perfect cube because the height is however wide you chose to make it, right? So if you did 5 of them, your height is 1/5. If you did 8 of them, your height is 1/8. Okay?
Because we're out of one.
Yeah, so we would do length times width, and since this is a square, that would be side times side, right? Because they're the same. So length and width are the same. We could call that a side. Whoa, wrong pen. That's a side, and that's a side, right? Times the height.
This is the first example.
This is the very first example, yeah. And this is the conceptual side behind it, okay? So what if I wanted to make, actually, let me ask this question first. What is the side length of each of these squares? Right, whatever the x or the y value is on each of these, right? So the y value here, the y value here, the y value here, the y value here, and the y value here. So if I wanted to find the side length of this side, it would be the y value at that point, right?
Yeah.
This point is 0, 2, okay? And so the length of this would be 2. If I want to find the length of this one, it would be whatever the y value of this point is. So it would be like 1/5. And then we plug in 1/5 into our equation. So 1/5 times -2 plus 2, 1.6. Okay,
Yeah.
so that's that point. And then this next point is 2/5. So it would be -2 times 2/5 plus 2 is 1.2. This would be 2/5, 1.2. Okay. And then the next one would be 3/5. -2 times 3/5 plus 2 is 0.8.
This is all under the assumption that I'm moving. You just
This is going down by point.
Yeah, this is under the assumption that I have a set width.
every.
Yeah, so this is the assumption that I split into 5.
Okay.
Yep. And then 4/5 times -2 plus 2. This would be 0.4. Yeah. And then this one didn't actually see, since we made this square, we made 5 squares. The last one ends right here. We didn't actually have a square here because that would be a square of 0. So if we wanted to find the volumes, we now have enough information to figure out, well, this is the length of this one, right? The first one has a length of 2. The second, so we could do 2 squared times the height, which is 1/5. And then we could add that to 1.6 squared. We could add that to 1.2 squared. We could add that to, we could add that to 0.8 squared plus 0.4 squared. And that would give us the actual volume of this solid that's like jagged, right?
Why?
Yeah.
Oh, okay, yeah.
I don't
understand like why it has to all be 1/5.
It doesn't, I just picked 1/5 because it's an easy number of width.
No, I understand that, but wouldn't it have to be like, you have to change it every time?
No, because the height is the width of each of these, the height, our actual height. So our area is the base, the area of the base times the height, right? The area of the base is that piece of paper that you made, and the height is the width of the piece.
Is it the width of this?
It's this width right here. That's 1/5, 1/5, 1/5, 1/5, 1/5.
See that?
I see what you're saying. So you're thinking that the width should be 2/5?
Well, no, like, shouldn't the height be that tall?
Yeah, the height is too.
Yeah, so I think you should change which ones.
I think he's asking like, why did you replace W as H?
So you're stuck on like the labels that I used.
I don't know.
Okay, so we could call this, the thing is that calling it something else kind of makes it hard to understand where we're coming from, but you could think of this as
I just think you should do.
Height.
The height. I think
Height.
it is width.
and then width.
It's just
It's
simply like.
Does that feel better?
How big that three-dimensional thing is.
Yes, the 3-dimensional thing is 1/5 wide. Yep. But basically, to find the area of the volume of this, we would multiply these two sides times the width of the 3D shape, right? Okay, so then if we did all of that, we could figure out this, and this would give us kind of, it wouldn't be a nice smooth thing, right? It wouldn't be a nice smooth curve like we saw in the animation yesterday. It would be like a jagged curve, right? It would be like square, 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 square.
Square.
Yeah.
Where are they rectangles?
I mean, these ones they're squares with, no, yeah, they're squares.
What?
They're not cubes, but they're squares, because these are squares. So it's like a square, and then the width. The width is not the same, so it's not a cube, but it's a, I guess technically a rectangular prism.
All rectangles are squares.
This is true. No, other way around. All squares are rectangles.
Yeah,
and
that's
all
what I meant. I
rectangles
meant
are
to say
squares. I knew
that.
what you meant. Okay, so this is the concept behind what if I just stack these? Well, now what if I cut this in half and now I have 1/10
more accurate.
It would be more accurate. What if I had 1/20th?
Oh, it'd be more accurate.
What if I took the limit as dx, the change in x approached 0, right?
What if
Yeah,
you just
yeah,
put it
yeah,
in
yeah.
the integral?
What if I just integrate it?
Oh my god.
Integrating it says, let
Well, I was trying to understand it on this level because I thought this is how it's gonna happen.
integrating it says, instead of
I was
doing
like, what are you doing?
big chunk, big chunk, big chunk, big chunk, big chunk, it says, let's make the smallest possible chunk we can get, right? A tiny, tiny, tiny little chunk, and we're gonna change it over time, okay? So how did we find the area of this? We took the change in x, right? Times the area of the base, which was that square, right? That was the area of the base. So we took the area of the base times the height, which is the change in x. So we did the area of the base times the change in x. That is where this integration formula comes from. This is the integration formula for any volume with known cross sections. You take the area of the base, so if you're doing squares, it would be the area of the square.
So then
So
It-
A is area.
The
A
area
is
of the
area.
two-dimensional.
Of the two-dimensional shape, yes. Because the dx, the dx is
Wow, it's changing from A to B.
the height, right? That gives us the volume. Or width, you can call it width.
Whatever. I don't know.
that's
I just imagine width, like, because it's going this way.
Yeah.
I mean, you could call it width if you'd rather, but that makes it
how
better.
wide it is.
We've just always talked about volume as area of base times height.
Yeah.
So you do have to think about it on the side. We can call it width, yeah, if that makes you
I
feel
guess
better.
it doesn't really matter because
I just hear
it's
height.
three sides. You just have to know the sides.
Yeah, yeah, and as long as you multiply all three sides together, you're fine.
Yeah.
Okay, so this is the area of the base times the width of the interval, and because we're integrating, the change in x is infinitely small, that's where the dx
You
is.
actually put a number in.
You do not, no, the dx is just to tell us we're getting infinitely small, we're getting infinitely close, okay? So, because we used squares on this one, the area of the two-dimensional shape that we used, that we stacked up,
Based on that.
was base times height, or side squared, right? So the area of the squares was side squared. And then we just do dx. Okay, and the limits of integration, since these ones are perpendicular to the x-axis, we're going to go x to x, right? So you can imagine us stacking them. So where did you stack the x first? At 0. And where did you end stacking x's? At 1, right? So you can stack. If you were stacking them this way, where did you start stacking? You started stacking at y equals 0, and you ended stacking at y equals 2. Does that make sense?
Mhm.
So the limits of integration are, where did you start putting your little pieces?
That's why it's 0.
Yes, so from 0 to 1 is where we started. We went left to right because we're stacking them this way, not up to down or top, bottom to top. Okay, so for this one, the integral formula would be from 0 to 1 of side squared. But what is a side? How long was the side of this? It changes every time, doesn't it? How do we find the area between two curves?
Find the area.
What?
We subtract them.
Look at this.
We subtract one minus the other, right? Like, how do I figure out how far it is from this point to this point? Well, I take the y value of this and I subtract the y value of this, right? Which would be 2.
Okay.
And then if I want to find the y value here, I would take the y value here and subtract the y value at the bottom, which is, yeah, it's,
All right.
1 sec.
You're doing the y value, you're doing the next
You're doing the y value, which is the function.
one. Okay, yeah.
Yeah, so how far is this? This is,
2x minus 2 plus 2 equals.
Yeah.
minus 0, right? So the conceptual side of it behind it is like, oh, we're doing, how long is that, right? The reality of it is really just top curve minus bottom curve.
Are we just not doing
I'll show you here in a second. So if you're trying to find the side or the base or any of these things, let me see if I have them.
we have to square it?
So up here you could write, this would be top curve minus bottom curve is going to be that length. So that's going to be like the side is going to be the top curve minus the bottom curve, right? Because that's how long it is when we
Oh, nice.
So here are we saying the bottom curve is? X,
0
0.
is y equals 0. Yeah. Yep. The bottom curve on this one would be y equals 0 because it's with the x-axis.
Why don't we?
So then we would integrate this from 0 to 1 at negative 2x plus 2 dx.
Dude, I'm running out of space.
And so all of that really just comes down to a formula, but there's a lot of information about why that formula works, and I think it's interesting to think about, and it helps you remember the formula.
Wait,
Oh, I forgot to square it.
Yeah,
That's
okay.
okay, that's what I was
that's
wondering.
what I was confused about. So
Why
I'm
did
putting
we
in
just square that?
R.
Oh, because we
Oh,
have two
so
sides.
S squared.
I forgot to square it.
Where did the 0 come from?
That's the bottom curve, because the top curve is this line, and where does it end? It ends
Yeah, I
at
was
0.
gonna ask that.
But then it's only finding the, oh, put it in the function. So every time we go up.
This is actually making sense.
Yeah, so if this maybe, say, instead of going to 0, it went to negative 1, we would do this line minus negative 1, or maybe it only went to 1, right? We would do this line minus 1. So wherever the bottom is.
Whatever our equation is inside.
Yes. Because the side is the top curve minus the bottom curve.
And
Okay.
the only time it would be minus something other than 0 is if we're starting somewhere other.
But like, how do you
Right.
know when it's like BH?
Like if you
the
have
example we had yesterday,
one, I was trying to see if I had one.
like the thing that you showed us yesterday.
Yeah, if there were two different lines.
I don't remember what.
So it's base,
It was like a funny shape on
and
G.
height is this thing.
Yeah, it would be the top curve minus the bottom curve would be the length of that piece that's going down there. Okay, so then we would just integrate it. So this could be, you could either multiply it out, so you don't have to do a U substitution, or you would do a U substitution to integrate this. Which would you prefer? Should we just multiply it out? So we have 4x squared minus 4x minus 4x, so minus 8x minus 4. Did I multiply it out right?
Dude, I wish I could just zoom out
Thank
and
you.
have exponentially more space.
Okay, and so then we integrate it, so we have 4x cubed over 3 minus
Or are you just doing that?
8x squared over 2, yes, plus 4x. When we get to more complicated ones, you just plug them in a calculator. Yeah. Well, you can see that if we got it right, okay?
I didn't.
So 4/3 x cubed minus 4x squared plus 4x, evaluated from 0 to 1.
Yes.
So we have 4x minus 4 plus 4, or 4/3, sorry, 4/3 minus 4 plus 4, so shouldn't it just be 4/3? Yeah. 4/3. Because when I plug in 1, I get 4/3 minus 4 plus 4. And then I subtract 0 because it's 0, 0, 0.
Cool.
So I get, our volume was 4/3, which if we had calculated, if we had had time to calculate those each yesterday, you probably would have found your volume to be about that. Right? So this volume, if we calculated this right here, we would get close to 4/3, but it wouldn't be exact because, right, we're overestimating. Some of those are way bigger than they should be.
So
It's
why
not
if we
smooth.
did it with geometry would it be?
If we did it with geometry,
Yeah, it's base times height divided by 2, and it'd be 1.
That's
2
You can't
squared
do it
Oh,
with
plus,
that's
geometry
the area,
because
it's
you
not
have to
volume.
have-
yeah.
you have to integrate it.
geometry does that. Calculus has 3 E's.
Okay, so if we did it with, if I finished out that bottom part that we did, right, where we did this geometry for this boxes, this actually equals 1.76. So if I tried to find the volume by just stacking little foam pieces on top of this, I would have got a volume of 1.76, which is kind of far off. I mean, it's there, it's close-ish, but it's not really. So calculus smooths that curve out and says we're gonna have an infinite number of tiny little squares instead of a few big
So
chunks.
it-
Well, that's.
what is that
that's
shape?
big
Is that
chunk
even
on
a
the
shape?
side.
Not really. It's not like a legitimate shape, no. Um,
Oh, you went there.
so like this is the one we were looking at yesterday. Remember, it had a top curve and a bottom curve. Okay, so this would be our XY plane. This is our 2D view, if I can get it to go right. There we go. 2D view is like this, right?
Yes.
Of the XY plane. Okay. We're going to put squares on top of it.
So we could do it with anything that we.
You could put literally anything you want on there.
That would suck so much.
So we're going to do equilateral triangles or,
I'm good.
okay, so if I stack squares on top here, I'm going to stack squares all the way to the end, and I'm going to do, like, we're going to start out with just a few squares, right? And you see how that's kind of a choppy, it's a very choppy size, because imagine that those are thick, right? But then it goes, if I keep stacking more and more and more, it gets to be very smooth, and it actually turns it into like an actual shape that there you can't even tell. It's just very, if you had an infinite number of squares, that's what the integral says. We're doing an infinite number of squares in between.
Wait,
Zero.
so where does the top curve minus bottom curve go when we like do this?
That would be the side of your square, or it would be like the base of your triangle.
So you would do that first and then plug in the equation into what you.
Yes.
So like you find the area of the bottom first and then you do the 3D.
Yes. Let's look at one. Let's look at this next one, because that might answer. Oh wait, that one doesn't have a top curve minus a bottom curve. Yeah. So your top curve minus your bottom curve is, so like if you have a base that you're trying to put on, you know, I mean, say you have some weird ones, right? So you have this curve and like kind of what we were looking at, right? And you're going to put a square right here. Okay, you're going to put a square right there. What is the length of the side of
Yeah,
that
like
square?
I get that, but like, where does that end up when we like do our integral?
So when we do our integral is the integral from, we can say a to b of the area of the base dx, right? Well, the area of a square is side squared. So it would be AB, and that would be side squared dx, right? What is the side of that rectangle, or of that square? The side of that square is top curve minus bottom curve.
Oh, so you just, that's where.
So that's where it goes, right? So if instead of a square, say you were putting like a right triangle on there, and right triangles are 1/2 base times height. So if you were putting a right triangle on there, we're going to do the same thing, but instead of the area of a square, we're not going to use the area of a triangle, which is 1/2 base times height. Okay. And it would have to tell you which one of, I guess it doesn't really matter. Say that the base is the one that's touching, right? The base is this one right here. Then we would put top curve minus bottom curve in for base. We would have to use something to, like, they would give us enough information to find that.
Like, example.
But the height would always be, oh, I guess. Yeah, the height would always be changing.
Typically, it's going to be, I don't think we actually deal with those ones. The height might have to use the Pythagorean Theorem. We'll have to look at some examples. I can't remember if you ever go that far. Sometimes they'll say it's an isosceles right triangle, and isosceles means the base and the height are the same, right? So if you had an isosceles right triangle, the base and the height would be the same. So you could, sometimes they'll put the hypotenuse on
What
it.
about when you do
Which is
like a
complicated.
circle or a semicircle?
Yeah, so a semicircle,
That's X and Y.
let's see, if this was a semicircle that we put on here, right? I might be able to draw a 3D semicircle. So here's a semicircle that we put on here, right?
Our radius is the top minus bottom.
Our diameter is the top minus bottom, right? So diameter would equal top minus bottom. So our radius
Is the
would
square
be divided by 2.
divided by 2. That's what I
Yeah, our radius would be divided by 2. So then we could do the same thing. Say you wanted to put a circle on here.
Why
Well,
would it be divided?
Because
Well,
diameter
it's got
is,
to be divided by 2.
right, because the radius is actually only half of it, right?
Pi of the square is right. Half.
Is the area of a circle, yes.
I
So
feel like
it's
we'll
half of
understand.
it. squared by 2. So don't you need pi and squared?
Yes, because you need the area of the base.
You got square.
The area of a semicircle is 1/2 pi r squared.
Yeah.
Okay. So the area of the circle would be 1/2 pi r squared. What is r? Well, r is top minus bottom divided by 2. So you replace that with top minus bottom divided by 2.
Okay.
Okay.
Do 1/2 pi.
Would the 1/2 inside just be like? a
They're
constant?
constant, so
So
you
just
pull them out.
okay.
Mhm.
top minus-
Yep, and because we're using semicircles, that's why it's 1/2 pi r squared, not just pi r squared. All right, let's set this up if we're gonna do instead of rectangles or squares, instead of squares going on there, we're gonna do semicircles. Okay, so we're going perpendicular to the x-axis, so we're still stacking shapes from 0 to 1, right? We start stacking them at 0 on the left, and we finish stacking them at 1 on the right. Now we need the area of the cross section. Well, it's a semicircle, and the area of a semicircle is 1/2 pi r squared. Okay? That should be dx. Dx. Okay? And now we have to figure out what is r. What is r for this one? Well, it's the top curve minus the bottom curve, right? Divided by 2.
I think you should give expanded space and minus zero.
I know. That's part of the reason why I gave you guys the extra work pages and stuff, because like Nate last year, it was his like goal in life to never, ever, ever write anything outside of the book.
I thought you said that was Levi.
No, it was mostly Nate. Levi sometimes did it, it was mostly Nate. Yeah. And so Nate would be like, I will get my homework in this space. I'm like, you don't have to. You can get another piece of paper. He's like,
You
no.
did give us a few extra. I literally have this much extra from
All the
of them
extras.
before I combined all.
Yeah, see, I think next year what I'll do is I'll just have the extra pages and you can add them in when you want, you know, instead of putting them in specifically. Okay, so R is the top curve minus the bottom curve divided by 2, because diameter would be top minus bottom. Yeah, so R is just top minus bottom, and so now I'm going to put that in. Yes.
The 1/2.
It does. No, because it's going to be squared, so it becomes 1/4. Yeah. So top of this curve was -2 plus, or -2x plus 2, and the bottom curve was 0, so it didn't really have a bottom curve. Because the diameter of the semicircle, if I put a semicircle on this, the diameter is this long. So what would the radius be? It would be half of that. That's why I divided by 2, because the diameter is this long, the radius would be half of the diameter.
Oh.
I think you're like trying to think of area and you're trying to complicate it in your brain, because the diameter would be the whole thing. So this one actually simplifies without that 1/2 ever. I'm going to just pull that 1/2 pi out, because that'd be 1/2 pi on the outside. Okay.
There is no.
And then this would be -x plus 1 squared, right? Because they divide by 2, dx. And then we just had to set that up. In this case, like sometimes you might have to integrate it by hand if it's something that's fairly easy. Sometimes you're going to get in your calculator to find that volume. But this would give us the volume of that solid.
How does not?
Yes, this one specifically says don't integrate, just set up. The pi is outside. I kind of had to squish it in there because, you know, I have so little space.
Yeah.
Yeah. Where did your? Oh, I see what you did.
Is it always? No. Can you guys show us how we would like do the pi and like would the pi go to each one of them? Like on each one of them?
Can we just integrate?
I know, but would
Do you want to integrate it?
Would
Yeah,
you
let's just
multiply it into each one of them, or would it just be the first one?
You would multiply it by everything, the
But
whole
then we
integral.
would get
So if I
through all
integrate
the
this would be the integral from 0 to
You don't
1.
need to be extra.
We're not being extra. We have to
X
do
squared
this
minus
eventually.
2x plus 1.
I don't think you need.
Okay, so if we were going to integrate this by hand, that's where we would expand that first, right?
Yeah.
And did I expand it right? X squared minus 2x plus 1. I think so. Okay, and then we're gonna integrate it. So this just stays outside. It's gonna multiply by our entire integral. So it's gonna be x cubed over 3 minus 2x squared over 2 plus x, evaluated from 0 to 1. So what you're asking, Casey, is does the 1/2 pi multiply by everything first?
Yeah.
You could do either way, right? Because you could evaluate this at 1 and multiply that by this, and then evaluate it at 0, multiply it by that. You could bring it in. I wouldn't. I would evaluate the whole thing at 1.
Okay.
So I would say like 1/2 pi. That would be 1/3 minus 1 plus 1. That's evaluated at 1. And then I would evaluate it at 0, which is just 0. And I would just do the negative 1/2 pi on the outside because that's easier than trying to multiply it. Then I would end up with, well, that zeroes out, that zeroes out. So I just get 1/6 pi.
That's stupid. That's small, that's a small volume. I don't like
It is
that
volume.
volume, that's a dumb volume.
Okay, I just wanted to make sure.
Like
that-
5-ish is 3.14 divided by 6 would be. Yeah. Okay, so if we want to do, here's, oh, you're fine. The next one talks about a rectangle with a height of 1/4, which is perpendicular to the y-axis, okay?
Dude, look at
So-
how much you wrote. Like, honestly.
I know.
Yeah, you have this much space. and you have-
I mean, you didn't have to integrate it, so I did that. That was all extra stuff because we
Me and Toby want.
Okay, first, let's figure out, so I just always write this down. I say, okay, it's the integral of the area of the base, and this is perpendicular to the y-axis, which says it's gonna be dy.
So are we going to have to
No,
What the heck did you just do? Did you go parallel to the x-axis? Is that what's going on?
I'm going parallel to the y-axis, so now,
No, what?
instead of stacking it parallel to the x-axis like I was before, now I'm stacking them parallel to the y-axis,
No.
okay?
Said it was perpendicular to the.
I mean perpendicular, sorry,
So now it's perpendicular to what?
perpendicular to the y.
So parallel to the x.
Yes. I was like, why did you say
Okay. I think the book really worded it weird, and Toby was looking at me strange when we were talking, so I don't understand what's happening. Like rectangles of height 1/4.
I haven't
Not
gone there yet.
perpendicular
Oh, I
to
thought
the
that's what
y-axis.
you did.
I'm just saying perpendicular to the y-axis. That's the only thing I've done so far.
Okay.
Perpendicular to the y-axis means I'm going dy, right? What are my limits of integration?
From 0 to
0 to 2, because I'm going from the lowest y to the highest y.
Oh,
Okay, because I'm stacking them starting at y equals 0, and I finish stacking at y equals 2. I'm stacking along y. So now it's a rectangle, so I honestly really do set it up this way. I write 0 to 2 of the area of the base times dy, and then I ask myself, what is the area? Well, the area of a rectangle is base times height, right? Okay,
so then if it says the height,
so the base would be right and left, I would say right minus left. Right?
So it'd be what?
We're doing triangle. No, we're doing square.
And the height for this one, they told us is 1/4.
Oh, you're doing 1/4 interval.
So this is the base, and then it only goes up
We're a rectangle.
1/4
I'm
off
not
the
the
page.
volume.
So instead of a square that goes up the same height, it's a rectangle where it only goes up 1/4.
What? Oh.
so we just distribute that right away.
Oh, okay, so the thing is like this. Okay, I get it.
Yeah, my 3D drawing is the worst. So it only goes up 1/4 off the page.
I got a
I'm
question.
talking about like.
Okay.
Like if you were to make
Yes,
1/4
Toby.
size.
So if we're doing ADY, do we have to change our function at all?
We do have to change our function in terms of
Wait.
y.
Here to Y.
In terms of y.
Height had to be the same as the like.
So Y.
No, this is a rectangle, not a square. The reasons we were doing squares, so we were doing base and height is gonna be the same. But we can't do the base as our right minus left, or like that, because that would be in terms of x, right? So what is our function in terms of y? So if we have
Y minus
negative
2
2x plus 2
Negative
equals y. Y minus 2 equals negative 2x. So we have x equals, we can write it a lot of different things.
Oh, yeah, I guess you could change the button.
Solving for x.
Oh, I was solving for y.
So I could write it like this. This might be the best, least like messy way to write it because I could just split that fraction because I can split numerators, right? I just can't split denominators. So it'd be negative 1/2 y plus 1 would be in terms of y.
No, we have to change that variable.
Yeah, so the base is not, it would be right minus left, and the right curve is 1/2 y plus 1, and the left curve is 0, right? The left curve is x equals 0. Does everybody understand why I have it in terms of y? And how I got it in terms of y? Okay, so from 0 to 2 of, and we could multiply that in if you wanted, but since we're just setting it up, you don't have to. And that could be it.
What I think we should integrate it just to see. Oh,
Let's look at another one.
I was with you there. It
Uh,
was just the,
Negative 1/2 y plus 1 times 1/4 dy.
okay.
So we could, again, we could bring the 1/4 out. We could have multiplied the 1/4 in. We could have done a lot of things here, but like this is the first thing, and so I would just leave it like that unless you were going to be integrating it. Yeah.
Cool.
Okay, let's try another one.
Hey, so why do we put the function as the
Because what is the length of the base? It would be the top function minus the bottom function. So we're looking for the length.
where we?
Yeah. Okay, so we're going to set up but not integrate an integral for the volume of a solid whose base is bounded by y equals negative x squared plus 2 and y equals x.
Okay, so
Okay.
of course you put this on this page, so now we even have less room.
Like I hate you.
I think so.
Yeah. I just lay it in bed and think, how can I make this student suffer?
Wait, do you make the book?
No. No, this was written by a guy named Gary Taylor. I like copied it. I mean, with permission. Like we bought a license to be able to reproduce it. Okay. So like I ran the copy. Okay. Do you guys agree that that's negative x squared plus 2?
Yeah.
Okay.
Now I'm colorblind.
Throw something at me again.
Again, yeah.
Let's see, we'll-
So, and then y equals x,
Yes.
okay? So the area that's bounded by that is this area right here,
Why does this make the rest? Oh, never mind.
okay?
we should get that over this.
And then it's asking us to make cross sections that are perpendicular to the x-axis, which means my cross sections are going to go like this. Yep, I'm gonna stack them this way. Okay,
Does it really matter where you?
no. Okay, so if they're perpendicular to the x-axis, everything's gonna be in terms of x. We already have all of our functions in terms of x, so that's a great start. We need to, the first one asks us to do squares.
Square.
Oh, it's only one. Yeah, we only have the one here. So squares that are perpendicular to the x-axis. So I write my formula every time from a to b of area dx. Because then it just helps me like fill it in, okay?
Like what you're doing?
Yeah, so the area of a square is side squared. Okay, and then I have to think, what is the side? Well, the side,
It's not.
no, it'd be top curve minus bottom curve, wouldn't it?
It'd be,
So the top curve, so I could even write this just to remind myself if I wanted, it'd be top minus bottom, negative x squared plus 2 minus x, right?
So you can put that in the integral just like that.
I can, yeah.
And then we need to find the intersects, right?
We do need to find the intersections, because where do we start and where do we finish?
We started to.
So I'm gonna just build right here. I'm gonna say, okay, my side is negative x squared minus x plus 2 squared dx, right? So I've gotten there. So I put in that for side, and then I put that in for area, okay? And now I need to find the intersections to figure out where I start stacking and where I finish stacking. So we're gonna set them equal to each other. Negative x squared plus 2 equals x. So I have negative x squared. Actually, I don't like negative x squared, so I'm gonna go to the other side. So I'm gonna have x squared plus x minus 2 equals 0. So I just put them all to the right side.
Oh, wouldn't it be minus x? Oh, wait, never mind.
Yeah, I did it like, and I flipped it in my head, but I thought I should probably do that. So I moved everything to the right side because I hate factoring when I have a negative in front of that x squared. So this factors to x plus 2 and x minus 1.
Yeah.
So they intersect at negative 2 and positive 1. Those are my x values. I don't need to find my y values because I'm only looking for this point, right? So I need this point and this point. This point is negative 2 something, but we don't care about the something. And this is 1 something.
Cool.
I mean, it would be negative 2, and 1, 1, right? Because y equals x.
What?
Yes.
Okay? Yeah. So now I just found my limits of integration.
So you could integrate.
They're negative 2 and 1 of the function, which is of top minus bottom, which was this, squared dx. It's not too bad, right? And then a lot of times it's going to be like, here's a calculator, solve it. Or, if it's solving by hand, it's going to be one that you can integrate pretty easily. Okay, last one, maybe. What time do we get out? 42. Oh, we still have 4 whole minutes.
You're the only teacher
No, this is
that
the
looks
last
at 4
one.
minutes and say, yeah, we can get something done.
This is the last one, and then all the people that are going to be gone tomorrow won't miss it. Okay.
I'm gonna be gone. No, I am.
Circles.
You know,
All right,
But you.
quit entertaining him and let's
Okay,
talk.
go there.
We got 4 minutes.
Okay, we're going to set up the integrals for the volume of a solid whose base is the circle. What? And whose cross sections are equilateral triangles perpendicular to the y-axis. Okay.
Oh my.
So
gosh.
it has a cross section that looks like this, right?
It's a cone, basically.
And it's perpendicular to the y-axis. Oh man,
triangles though?
they're triangles. So here's the problem. What's the right curve and what's the left curve? There isn't one, but there kind of is one. Okay. Okay, A to B of the area of the base dy. We'll start there. Okay. What's the area of an equilateral triangle? It's up here on your thing, root 3 over 4 side squared. Okay. Here's the problem. What's the side of an equilateral triangle? Well, there isn't a right curve minus a left curve yet, right? Because it's this point, whatever this point is, minus this point, correct? That's how long it is?
Why can't you just go from 1 to 1?
Because it's not always one.
Well, as a starting point.
But we need all of them. We need infinitely many ones. So here's the thing. We're going to make this into 2 different curves.
Here we are.
So we're going to solve for it in terms of y. We got to get y by itself. Or no, we got to get, x by itself because we need it in terms of y. So I'm going to get x squared equals 1 minus y squared. Do you agree with me so far? Then to get x by itself, I'm going to take the square root, aren't I?
Yeah.
Okay, and that would be plus or minus
No.
the square root of 1 minus y squared, right?
No.
Guess what? The plus side is this half of the circle. The minus side is this half of the circle.
Okay.
Okay, so this is the plus side. So this is root 1 minus y squared. And this side is negative root 1 minus y squared. Now we have a right curve. We have a left curve. So our side.
He sounded like Saul from Comic.
Oh, I love him.
You guys don't know Saul.
He was my savior when I was taking calculus for the second time, or for a long time since I had taken it. Okay, so we're going to do right minus left, right? So the right curve is 1 minus y squared. The left curve is negative 1 minus y squared.
Why is it? Okay.
Okay? So really, the side is root 1 minus y squared plus root 1 minus y squared, which is 2 root 1 minus y squared. Because see, there's two of them and we're adding them together. So now we go from a to b of root 3 over 4 to root 1 minus y squared, because that's the side, dy. Okay? And then from negative 1 to 1.
And you, what was negative 1 to 1?
What's the farthest left? This circle goes just negative 1, and what's the or sorry, not left and right, bottom to top, because we're going perpendicular. Where did we start stacking equilateral triangles? We stacked them here, and we went up, and then we started at negative 1 and finished. And then rectangulars, we'll talk about that tomorrow. Rectangles that are whose heights are 3 times their base. We basically have done everything, all the setup we need.
Wait, when did we decide that it was negative? Oh, because it's right.
Who's gonna be gone tomorrow?
And no.
Oh,
And me,
golf.
and I think golf and track.
Okay, really quick then, I guess if you want to do this one, ready? What would
I
the
didn't figure I just closed it.
the area of a rectangle be? Base times height. The base
Oh, wait, I haven't do it.
The base is this side, right, that we just found? That's the base. And then it says the height is 3 times the base. So if we already know the base, we also can find the height, right? Like, because it's 3 times that.